Hey. Okay. So my name is Sam Falvo. I'm the person who typically does the Kestrel stuff, but I don't have anything Kestrel related because I'm just taking a break from it right now. And in fact, somewhat relevant to that, I wanted to write a Space Invaders clone for the Kestrel 2DX. And in coming up with thinking about how to write the game or how to encode the rules, I found myself writing code which was very APL-ish in nature. I would end up writing things like, if the vector comprising of the tail ends of all these different rows contains, at least one alien in it, then I know that the aliens have reached the far end of the screen, and then I should just, step them down one and march them in the opposite direction, that sort of thing. And I found myself, as I tried to transcribe that logic into Forth, I found myself pining for having the ability to express the game logic in a single line of code, which APL is quite well known for. So that kind of brought my mind back to a project that is not mine. It is actually from Bob Armstrong. Bob Armstrong is a software developer who is well-rooted in the APL and the K communities, and I guess relatively recently, not necessarily in the last couple of years, but I know he's been working on this particular project for quite a while now, but in relative terms, this is his newest project, I think. He has a project called CoSy, which he transcribed into Riva Forth. CoSy itself actually goes back to, forgive me, Bob, I'm probably misremembering, but at least the early 80s, when he wrote it in actual APL, and then later transcribed it into K, which is Arthur Whitney's derivative of APL, and now into Riva Forth. And what CoSy is basically, it's a vocabulary written in Forth, as you might imagine, which implements a large subset of the vector processing words or functionality that you would find in something like K or APL. And by which I mean you could actually write vectors. You can have, for instance, I open paren 1, 2, 3, 4, 5, close paren I, and that would actually put a vector 5 long into memory, and with that you can actually do vector mathematics on it, or you can iterate over each element, that sort of thing. And that's kind of what I wanted for writing my particular game. I knew it would not run very fast, but I didn't care about that. I just wanted it to be correct. I wanted to know, get it working first and then optimize later, that sort of thing. And so I started studying the code for CoSy, and with my specific interests in mind, my connection has timed out apparently. So yeah, lovely. Yeah. Unfortunately, it won't allow me to do that because come on.
By the way, pickdog.org. It's a shadow of its former self, but it's fun.
Here we go. So this is basically the source code. It is up on GitHub. I'm going to zoom in here. And as you can see, it's somewhat unconventional. It's definitely not ANSI Forth. It is RevaForth is itself a derivative of RetroForth. So it has a lot of RetroForth style legacy to it. For example, the vertical bar instead of the backslash to indicate a comment. But to any competent Forth programmer, when you look at this, it's very obvious things work. So what I wanted to do is I wanted to study this code so that I could kind of shamelessly steal from it. And as I was getting into this, I was realizing more and more that, oh gosh, you know, this thing is, when I scroll down here, like for example, where am I looking at here? So there's various, so here's where it starts talking about the headers and such that describe it in memory, and I'll kind of get into that a little bit. Generic memory allocation, accessing individual elements, and I'm kind of breezing through this deliberately, but I'll go back to some of this stuff later. And then, like, as soon as like, very small number of lines of code later, we're starting to describe things like nil, and then generic cell vectors, and then from there we're going on to the various different types, of one of which is the integers. Later on down the line, and so on and so forth, there's strings and so forth. And it turns out that when you're trying to do real-world programming, not just programming games or whatever, what's the number one thing that you're going to be dealing with? Strings and quantities of integers and stuff like that. So I'm looking at this, and I'm realizing, especially when I scroll all the way to the bottom of the listing here, and there's a lot of headers and include files and stuff like that, but this is the guts of everything, and it's less than 1,700 lines of code, including comments, including white space. In absolute terms, compared to most Forth libraries, this is gargantuan in size. But compared to, for instance, an actual implementation of APL, this is diminutively small. So I'm actually kind of, especially for the Kestrel 3, not so much the Kestrel 2DX, because I don't have the memory for it. But with the Kestrel 3, I'm kind of interested in porting the guts of CoSy and actually incorporating it into the Forth environment that is going to run on the Kestrel 3. If I can swing it, I might also do the user interface part, because CoSy is not just the vector facilities, it's also the workspace environment that is largely borrowed from original APL. All right, so I'm going to try to, so I've been studying this code for just about a week now. And so I'll kind of start here. This for constant head number. This is describing a prefix to a vector of stuff. Whatever that stuff may be, doesn't really matter. They all have a common header to them. And this header is what allows you to mix and match types dynamically at runtime. This is what makes it dynamically typed, if you will. You have a couple of accessors here, which I'm not entirely sure the exact layout. It's actually documented on Bob's website if you follow through the links enough. But long story short, when you actually allocate a new vector in memory, what you're doing is you're basically you're making space for that header, plus including all the amount of bytes needed to allocate the body of the vector. You just allocate it and then zero fill it with default values, because otherwise you'll end up with a vector full of random data. He has a convenience word here, iNumber. You'll see this frequently. Basically, this is an array accessor. But then we see down here, like vresize. This is used for when you create a static vector in source code, like the I open paren and then the stuff there. that actually fills, the way CoSy works is it actually fills in a statically allocated vector of about 100 or so integers, or 100 cells, thereabouts. And then it basically copies that into dynamically allocated space using this V resize, which is kind of convenient. IX is interesting. This is the core of accessing a vector element. And basically what this does, this is the magic line right here. The top line is basically error checking. But what this does is it uses modulo to constrain your array index here to the number of items that's actually in the array. So if you happen to have a vector of 1 and you're applying this vector, say you're adding this to a vector of 8, for example, it'll actually attempt to index this one length vector using indices 0 through 7. But it will always end up accessing that one single element. So if you're familiar, for example, with Chuck Moore's circular stacks, it basically behaves in a similar way. So you end up using, if you pass in a 3-length vector, it'll go 0, 1, 2, 0, 1, 2, 0, 1, 2, and so on and so forth. It'll keep looping over your source vector that way. And a lot of what this allows is, for example, like I was saying, if I want to take the sum over items within, a particular row of Space Invaders, and I want to say, I want to make sure that that's 0, otherwise it's the end of the game, then I can say 0 equals, the name of that vector, and it will attempt to compare 0 across that entire length of vector, and then I sum the results from that. I don't have to pre-allocate a length of 40 or whatever zeros first. Like the modulo means that I can work around that. In terms of memory management, it is reference counted. This is some of the logic that goes into that. And I'm sure that I probably breeze over this because my mouse pad is not behaving quite right. But when you create an object, now CoSy, when you first create an object, creates it with a reference count of 0 initially. That's one thing that I don't like. Typically when I use reference counting, I always create it with a reference count of 1 just to be on the safe side. But in practice, I guess it doesn't really matter because when you actually go to store it or how he has his stack primitives, that ends up getting accounted for. So for example, when you look in dupe plus, for example, it's a reference incrementing version of dupe, meaning once you duplicate it, you increment the reference count. Likewise with this reference counted version of over does the same thing. And the idea is if you no longer have a reference to it, you execute this another word, which I believe is, I want to say ref minus. I can't really find it right now, but it may be further down in the source code. But there is a word that actually releases a reference count, and once it reaches 0, it will properly deallocate that particular vector. Now this particular, this vdupe is interesting. Returns a copy of an object. Now in APL, a vector is not a reference type. So you could have a vector of 256 integers, and if you want to make a copy of it, say A equals B or A becomes B or whatever, it will actually create a copy of all 256 elements. This is actually something of a performance sink. So if you're doing high response time programming like video games, like my interest is, this would actually be a performance killer. For scientific work, for financial work, it's not really a big issue because your vectors are going to be so long anyway that the time spent copying versus the time spent actually processing them is going to be much more to your favor. So I'm going to try to experiment with reference types in my particular application. So here's a short word, _I. You'll see this a lot in Bob's example code. Basically what this does is this takes a single integer and wraps it into a length 1 vector, basically. This is more of a convenience word because a lot of these words only accept vectors as inputs. Enclosing and disenclosing. This is kind of hard to explain without really knowing more about the APL's original way of structuring memory, but basically what this allows you to have is a vector of references to other vectors. This is how you form more general data types. For example, I can have, as my first couple of elements, I can have a username, a password, an email address, and a person's phone number, for example, right? So all of those are different types. They can be different lengths. And in a vector language, typically this would be like a hard-coded rectangular array, that sort of thing. And the way the original APLs worked around that is by what's called boxing or enclosing. This is that exact same kind of logic, but in the K programming environment, this is very implicit. So you still have enclosing and disclosing, it's just happening behind the scenes. And this is the logic that kind of makes that happen. For example, here's enclose atom. Basically, it does a check to see if it is in fact, if it is an atom, then go ahead and enclose it. Otherwise, just leave it as is, basically. Here we go, reference decrementing. This is what I was talking about earlier. This is actually a fairly sophisticated chunk of code because when you have references to other references, what happens when that root level reference reaches 0, right? You have to go through, before you deallocate that initial vector, you also have to deallocate, or at least dereference, all the children nodes as well. And this can happen recursively. And so because this happens recursively, you end up with a fairly sophisticated chunk of code. Not very many lines, but if it takes some study to actually figure out what's going on. So then we've got a chunk of code that's relevant to temporary parameters. He has parameters like T0, T1. These are just variables, basically, that you can assign to. They're like Chuck Moore's A register, so to speak, in a certain sort of sense. And as you can see here, it is interesting that whatever was originally in T0, when you assign to it, it automatically gets dereferenced. We then reference the object that's currently on the stack, and then we stuff it into memory. Right, so this way here, you don't have to manually do reference counting and that sort of thing. You'll see references in Bob's source code, for example. You'll see references to R0 and things like that. Same idea. T0, T1, and R all have the same basic behaviors. Very commonly used constants, just like how originally in Forth you have constant 0, constant 1, constant -1, that sort of thing. These are the same things, but they are vectorized. So you have I0, I1, and I-1. And here's where the magic really happens. We've got, I haven't quite fully decoded how the naming convention here, but each M and each D refers to a monadic or dyadic function that you want to apply to every item in a vector or a pair of vectors. Monadic referring to single parameter, and dyadic referring to taking 2 parameters. And we see that here in the monadic case, we take one particular vector that we want to operate on, and in the dyadic, we see that we take 2 particular items on this as inputs. And what we see is we've got this IC fetch that's being used. Here we've got IC fetch being used on both the right hand and the left hand vectors being used before we execute our function. And then based on that, we compose a new vector accordingly. That new vector is initialized here. And there's similar logic up here if you study it. For example, we duplicate, basically use vdup to do the duplication there. It should be interesting to note, in the dyadic case, the resulting vector is always the longer of the left-hand or the right-hand vector. This makes sense because when you iterate over the loop, that modulo indexing will automatically extend the short vector to fit the long vector. That's kind of what I was talking about earlier. So I think the MCR and the DCR, well, I explained the M and the D. The C part of the name, that middle part there, that refers to a generic cell. So these functions will work with any cell-sized vector of data. The I part refers to integers. Later on, he also has functions for strings as well, text strings, which are basically bite-sized units. So here's the code that I was talking about when you say I open paren. This is actually a forward parsing word. And when you execute it, it basically checks to see, is it the closing token? And if not, interpret it as a number and stuff it into a particular vector. But the thing is when you look at the initial vector, if I'm understanding this correctly, he's allocating 100 kilobytes for the vector up front, which should be plenty of memory space for any reasonable sized literal vector. When he's done with that, he will resize that vector back down to something more suitable for the vector that you actually gave it. So row is, this is a common idiom in virtually all APLs, both APL itself, APL2, J, and K, all have this symbol or something like it called row. And its purpose is to tell you how big this vector is, how many elements are actually stored in that particular list. In actual APL, it can also be used to tell you the shape. In fact, you'll hear it referred to as shape. And its result will actually be itself an array. It's a 2 by 3 by 4 matrix, for example, cubical matrix. K doesn't really deal with that. And likewise, CoSy doesn't deal with that either. It greatly simplifies the problem space to just dealing with lists of lists. And so since you're dealing with lists, that implies that you only have one dimension to think about at any given time. So in this case, row just returns a very simple integer on the stack. Now, these are operations that make use of the each operators that I was telling you earlier. So if I have an integer vector, 1, 1, 1, 1, 1, and I have another vector 2, 2, 2, for example, and I add these are the operators that I want to use. And what this does is this basically binds fourth's built-in plus operator using each dir, in this case, to compute the vector sum of these two operands. And there's plus, minus, multiply, divide as well, modulus, minimum and maximum as well. Here's a bit of syntax that, as far as I'm aware, is unique to Riva, and that is you can define multiple synonyms for the same point in the code, the actual same definition. There's a different part of the source code which confuses me, where he uses colon, the name of the word, colon, and then a number. That kind of confuses me a little bit. It seems to, what's the word I'm looking for? It seems to contradict my interpretation here. So I'm not entirely sure yet how that works. But long story short, and again, here we're saying, check for equality between element-wise on the integers, that sort of thing. So yeah, I've only been studying this for a couple of days now. I'm not like an expert at this code at all. Concatenates integer vectors. So this is code that we'll take two integer vectors and we'll splice them together into a single list. And there are character equivalents of this as well, CL, I believe, that will do the same, which is incredibly useful for text processing and things like that. And speaking of which, there's our byte vector creator. And we have IB fetch and IB store, same idea here. And in this particular dialect, S-quote is being used as the word that creates a string vector. S-quote, unfortunately, is already taken by ANSI forth, so my port of this will probably have to change the name of this word, which is unfortunate. But at the same time, it'd be also very convenient to go back to just using quote as well, because I kind of miss that. $sign quote's another option as well, yeah. Symbols are basically internalized strings. They're basically a very specialized form of strings in a sense, I believe. And then we get back down here to a bunch of vector symcat. I believe this is concatenation. Yeah, so Yep, so he's adding the lengths of both vectors here. And down here, I'm sure we'll find, I thought I would see CL, but maybe that's in an included file somewhere else. But he does have, a bunch of different emitters and outputters and things like that, convenience functions. And he also has definitions as well for floating point as well. But basically, you look at this and it's, all of this has a very certain sort of structure to it. It's very uniform structure is what I'm trying to get at. And for any given particular type of vector, the code has the same basic shape, same basic iteration mechanisms, the same basic memory management tools, that sort of thing. Here's IOTA, which in APL is popular because basically this is how you generate numbers from 0 to some number, which is often used as initialization code for building out matrices and that sort of thing. And as you can see, basically all this does is it just initializes a vector of integers of certain size, and it just fills it in with sequentially incrementing numbers. There's our dyadic and monadic functions in the floating point domain, various min-max, that sort of thing. I'm not entirely sure what this stuff is for. I haven't quite gotten this far yet. I think what this is happening here is basically if you give it a generic operation, it will attempt to determine which accessor to use based on the type of vector. So this is a generic fetch function, for example. Yeah, and then here we have each M, which is probably the version of each that you'd want to use in the general case. And what we find here, over execute loop drop refs. Okay, yeah. So this is basically just doing the same thing that this more specialized each M stuff happens to be doing up above. Exactly why this is broken out, I'm not quite entirely sure. I haven't gotten that far yet, as you can tell. Integer functions, floating functions. Again, this kind of looks like the code that will select the appropriate operation depending on the specific type. vector that you're working with. And then here's a different variant of each M. This actually appears quite frequently. So yeah, okay. So here we're actually looking to see, we're actually starting to dispatch on specific types now. So this is probably the topmost item that you'd want to use if you wanted to apply a function to each item without concern for specific types used in vectors. And then each is the dyadic version of that, by the looks of it. This is the atomic apply. I think this created a bit of I won't say controversy, but certainly some discussion on the fourth mailing list recently. And I think what this does is it basically iterates and recurses into lists until it finds a non-list item, and then it applies a function. So you could say, I want to execute the word double, for example, to multiply something by 2 on an arbitrarily deep set of lists, for example. That I believe that's how this code works. And then there's the dyadic version of that as well. And I think the rest of this is more general purpose accessors, iterators, that sort of thing. I'm not quite sure how these across, I think some of these are scans as well, if you're familiar with APL scans. That basically is a running sum instead of, so typically when you do a reduction on something, it's like inserting a plus say add reduction. You're basically saying if I've got this vector of 4 items, 1, 2, 3, 4, it's like saying 1 plus 2 plus 3 plus 4, right? A scan is a vectorized version of that where you start with just 1, then you compute 1 plus 2, then you compute 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4 is your final item. So yeah, so here's our initial definitions for scan, I guess. So yeah, this is actually relatively clean code. I mean, if you're not familiar with the concepts of APL, this could certainly seem very opaque. But since learning J and myself some years ago, I understand a lot of the idioms that's being used here. The pieces that I still have the most uncertainty about is, for example, when I see a large body of code like this, like SS, lower swap, colon, CSS, you know, like I have to sit here and I have to basically parse through this code and actually just kind of sit there and study it and see what it actually is doing. Like it says here, modeled on K's underscore SS function. Well, I don't know K, so I have to kind of reverse engineer that. But there are certain things in here that do stand out to me as well. I've actually tried to apply what I've learned to my own code, and I hope that I can illustrate that here. So this is code that I've written in G4. There we go. Let me turn off syntax so that you can actually see it. So basically this is, and again, this is not my attempt to replace CoSy or anything like that. This is just my attempt to better understand by copying, basically. And so I have a different length header. I've got 3 cells instead of 4. Reference count, the size of each element in bits, and then the length of the vector in elements. You multiply those two and then divide by 8, and that tells you how many bytes the vector basically is, not including the header of this as well. And it's basically the same idea. I've got some G4 specifics, valloc, vfree, that sort of thing. I do differ from Bob's code in that when I construct a statically allocated vector, I do so at here. I do not dynamically allocate a vector first. So that if you see references to here and comma and all that other stuff, that's where all of that is happening. And then I execute restore to free the memory when I'm done using it. I have support for integers. I've got support for what I call characters, which are just 8-bit bytes, but that are not intended to be interpreted as a string. And then I've got vquote and vtick to serve as vectors for strings. And then I've got the ability to dynamically create a vector. I've got some reference counting logic. And then that's basically as far as I got. So that's kind of the CoSy code that in a nutshell. Not terribly exciting, I guess, because this is all black magic that happens behind the scenes. But it is the very foundation and the very core of what makes CoSy as a vector environment and forth interesting. And it's also very interesting because if you want to understand how APL works or how K works or something like that, this is actually very approachable code. Whereas if you wanted to look at off-the-shelf stuff, you're looking at C code, which is incredibly dense and written by APL programmers. So there's like no white space to help guide you in reading the corresponding C code. So this is just my attempt at cloning it for my own understanding. Any questions? Looks like I'm done then.